Blessed is the man who does not walk in the counsel of the wicked, or stand in the way of sinners, or sit in the seat of mockers. But his delight is in the law of the Lord, and in his law he meditates day and night. And he shall be like a tree planted by streams of water, which yields its fruit in season. His leaf also does not wither, and whatever he does prospers. Not so the wicked. They are like the chaff which the wind blows away. Therefore the wicked will not stand in the judgment, nor sinners in the assembly of the righteous. For the Lord watches over the way of the righteous, but the way of the wicked will perish. Okay, now we are working on 65B, which is talking about the graph of the exponential versus the logarithm. We've talked about exponential curves. Now let's look at this one down here before we go up here and look at the general definition here. Please be quiet, whoever's making the noise. Thank you. All right, so here we go. If I were going to graph y is equal to 2 to the x, what will I start with? I plug in my x, I plug in my y. Y is a function of x. If I plug in a 0 for x, what is my y? Mark.
0.
Oh, is it?
1.
2 to the 0 is? 1. Very good. Okay, if I plug in 1, Zach? 2. Very good. If I plug in 2, Ben? 4. If I plug in -1, Wes?
1.
No, -1, Wes.
Oh, 1/2.
1/2?
Zach was.
Okay, what if I plug in -2? Peter?
Oh, 1/4.
1/4, very good. What's going to happen if I plug in -3? Susie? -3, if I plug in -3. Huh? 1/8. Thank you. Okay, so when we graph these points, 0, 1, 1, 2, 1, 2, and 2, 4, we get this curve that's going up. Okay, this is called an exponential curve. Okay, and it's going up exponentially, and it's going to always follow this pattern. But to the left, as I go to -1, I might dip down a little bit farther than it's looking here. I go to -1/2. I go to 1/2. If I go to -2, I go to 1/4. And I'm going to continue getting closer and closer, but am I ever going to touch that line? No, because if I do 2 to the -100th, it winds up being 1/2 to the 100th, which is a very big number on the bottom. But it's still not 0. Okay? So it's going to go on that sweep, and when you know, my phone rings. Ring, ring, Carl.
Ring, ring.
Is it 102?
102.
0.
I haven't gotten any official, but she's not.
Oh, wait, no.
Thank you.
102.
Okay, everybody look at this one. Okay, how would I graph x is 2 to the y? Okay, so let's do the same thing. And what did I do? This is y is 2 to the x. I just switched the x and the y. Okay, and when we do that, we're going to get the inverse function, aren't we? When we switch the x and the y, we get the inverse function. So let's graph this inverse function. All right, so I'm going to make my little x and my y. This time, x is a function of y. Okay, so we're going to plug in 0 for y and crank out a what? A 1, right? We're going to plug in a 1 for y and crank out a 2. A 2 will crank out a 4. A 3 will crank out a 8. And then a -1 will crank out a 1/2. Okay, so now what is this looking like? 1, 0. Notice that on this graph, all of the points are switched. 0, 1, 1, 0, 1, 2, 2, 1. All right, so now 1, 0 is there. 2, 1 is here. 4, 2 is here. Okay, then go down to 1/2, -1. 1/4, -2. And it's going to asymptotically approach that line and look like that. Now remember, yes?
So when we switch the y and the x, it's gonna be like a reflection of the.
An inverse function is a reflection across
Yeah.
this line right here. So let's take that graph now that I've done them separately, and let's put that graph right over here so that you can see the two together. Reflect across what line?
Those Z axis.
Y is X.
Yeah.
Okay, the Y is X line is like the identity line. It's called the identity function because everything is equal on both sides. And it is going to, all of your inverse functions will reflect across that axis. So what they're trying to show you is when I rewrite, remember what a logarithm means. If you go back to the definition of the logarithm, if I have a y as log base 2 of x, I can write that same logarithm in an exponential form that is 2 to the y is x, which is exactly what we graphed right there. Okay, so a logarithm, y equals log of x, is simply the exponential inverse where I've switched the x and the y axes. All right, notice that this graph, the exponential graph, is curving around the y-axis, whereas this logarithmic graph, this is the logarithmic graph, it is curving around the x-axis. The axes of orientation have totally switched between the x and the y, and this is always going to be true for exponential and logarithmic graphs. So what they're showing you up here is kind of the basic definition. If you go back to the basic definition of logarithms, they would say in the basic definition that here, remember the log is the exponent to which I raise the base to get the argument. Okay, let's say it again. I want you to know that definition. The log is the exponent to which we raise the base to get the argument. Chris, I didn't hear you. The log is the exponent to which you raise the base to get the argument. Okay, so here they're having the definition right here. The log is the exponent. Now, if this whole thing is log, then this is log. The log is the exponent. So what's the exponent?
The log.
L. Here, in this definition, L is the exponent to which I raise 2 to get the argument. So I would have n equals 2 to the L, right? 2 to the L. If I were going to turn this statement around into its exponential form, it would be base raised to the L log here is n. Or if this was a y and this was an x, it would look like what? X is 2 to the y. All right? So if I had that logarithm, that's what it's going to look like if I was in the xy, which is more familiar. But this is the exponential form of this one. All right? Then what did they do over here? All right? This is the exponential form. The log 2 to the L is n. All right, so this is the logarithmic form, and if we were going to turn it around to solve it, we would use this, okay? But notice in the two graphs on the board, and this is what I think is really confusing in the graphs, okay? Notice on this page that I said was so easy, and I understand why it's not so easy. Look at these two graphs. They have switched the axes on these graphs. And when you look at it, you don't see it. In other words, on this graph over here, they have made this the L-axis, and they have made this the N-axis. But in this graph over here, they have made this the N-axis, and this one the L-axis. All right? So they're not graph. When you look at this one, you say, oh, this is N is equal to the 2 to the L. That's because this is the N-axis. Just like that was X, this is the X-axis. But here, they flipped it around. And they made, if I were to graph this function, I mean, if I was going to look and say, okay, let's do this graph the same orientation as that graph. Let's do that. Okay, that's why this one looks flipped of that one because this is n is equal to 2 to the L and this is n is equal to 2 to the L. But in your book, they flip the axis. So let's change that. Okay, let's go to where they actually look like they're supposed to. All right, so if this is this function in its exponential form, and I wanted the inverse of it, then I would flip it around and I would have what? L is 2 to the n. And if this was still the n like it was over there, and this was the L like it was over there, and we didn't switch axes on you, then this one would look like what? If I flipped it around, then I've got, if I plug in a 0, I get out a 1, right? So 0, 1. It's going to go this way. The confusing part is they switched the axes in the book. I think that was just, I don't know why they did that. I think they're trying to show you the inverse relationship. But to me, that part is confusing. Okay? All right, everybody look at the exercises over here. And once you understand that they are flipped and that they are going to be reflecting across here, logarithms go this way, exponentials go this way. It's very simple to graph them. But your first problem here says that you're supposed to graph y is equal to log base 3.5. Log base 3.5 of x. Okay, so if you make your little grid, you're going to have 0, and it doesn't matter if I change it, it's often easier to graph it in its exponential form. So that would be 3.5 to the y is x, right? The base raised to the log is the argument. So then I plug in let's do the y here, 0, 0, and then I go to 1. If I plug in a 1, I go to 3.5. Okay, so I've got 1, 0, and I've got 3.5 and 1. And my logarithm is going to, oops, that didn't work. My logarithm is going to go that way. Okay, so you only need, if you know what logarithms do, you only really need a few points to graph them. And because it's a logarithm, it's going to go that way. If it's exponential, it's going to go that way. Yes?
I heard that logarithms they're used in video games because one of my cousins we were just talking about it. So how would those lines help design the games?
Logarithms are really, really cool because they allow you to do much more complicated math with simpler operations. Okay? When we went to the moon back when I was young, a long, long time ago, we went to the moon on logarithms. We didn't have these supercomputers. We had a bunch of guys using slide rules and logarithms to get this stuff done. So logarithms are a very, very powerful math tool, okay, that you're going to use a lot in all kinds of applications. Medical applications, engineering applications, a lot of applications, all the way through. So they're using in the programming, I'm sure, they're using those functions, and I don't know exactly how, yes?
But when you were working can you show an example how would you direct a rocket in some place with logarithms?
Okay, when I was modeling rocket ballistics, we were using a lot of quadratic equations, okay? And you can use, as you're working with things, you're going to find that you can use shortcuts to solve even more complicated equations. So we were using quadratics because we were talking about something goes up and comes down. Okay. Now a logarithm doesn't go up and come down, so we wouldn't use a general logarithmic equation to model a missile ballistic. Okay, unless you were talking about something that was going to go like that and stay going up forever, that would be something that would be more logarithmic that you might model with a logarithmic curve. Okay, but a lot of things are logarithmic, and we're going to talk about them in the book, and we talked about them in Algebra 2. Population growth is often modeled with exponentials and logarithms. So like a decay might be exponential, but logarithmic comes in a lot of medical applications and things like that. pH, when you're doing litmus testing and pH, there's a lot of things that do lend themselves to be modeled by a logarithmic function. So you're going to see a lot of growth decay type stuff that will use exponentials and logarithmics to get them solved. Okay? So, let's look at the next section here. Everybody go over to 66. And then we're going to break off and do our homework because we didn't get to that yesterday. Now, what I want you to do is I want you to take these quizzes home tonight so that we can spend some time tomorrow reviewing for the test, which is Friday. Okay, yes, Suze? Yes. All right, so formulas for systems. Formulas for systems of equations, phase shifts, and period changes. Okay? All right, so we're doing x equals b2 c1 minus b1 c2 over a1 b2 minus a2 b1. Okay? Now on this one, this is basically what they're doing is they're talking about solving simultaneous equations, and we're going to find when we get to Kramer's rule that there's a pattern behind these. So they're starting out with a1x plus b1y is c1. They're talking about a generic pattern here, okay? And then they've got a2x plus b2y is c2. All right, and they say, let's solve it for x. Solve for x. Okay, and this one really goes with abstract systems of equations where you don't have the actual numbers, okay, but you have to solve for a variable. So if I was going to solve for x in this one, solving for x, then I really want to first just get rid of y. Yes?
So multiply the top by b2, multiply the bottom by negative b1.
Okay, right. So I'm going to multiply this one by b2 all the way across, b2 all the way across, and I'm going to multiply the bottom one by negative b1. And then my b2, b1 and my negative b1, b2 is going to cancel out and when I add them together. So let's go ahead and do that multiplication, and we get a1, b2, x plus b1, b2, y equals b2, c1. Then down here, I'm going to get negative b1, a2, x plus, minus b1, b2, y is negative b1, c2. All right, so now these are going to cancel. Yes? Okay, so now what's David?
Huh?
Now what do I have?
You take x out of,
Well, let's just add them together
add
first.
them together first.
So I got a1, b2, x minus b1, a2, x equals b2, c2, c1 minus b1, c2. Right? Okay, so now I'm trying to solve for x.
You divide the left side by x.
Right, we're going to factor out an x, right? That's what we're doing. So we factor out a1, b2, x minus b1, a2, x equals b2, c1 minus b1, c2. Okay, and then we end up with x equals
b2, c1 minus b1, c2 divided by a1, b2 minus b1.
Okay, somebody find the section that talks about Kramer's, because I'm going to show that to you at the same time. We're just going to do that one blended in with this lesson. Somebody look up Kramer's in the back and take me to the Kramer's section. Now notice, so this is what I have.
I still have an
C-R-A-M-E-R, I think. All right, so.
It's like Kramer, but
Yeah.
without the E.
All right, so this is how we got x. All right, then.
Less than 70. Let's say it's
Ooh, I
Lesson what?
74.
74.
74. Everybody turn over to 74. And we're just going to look for a second at Kramer's rule. Okay, so we're kind of blending these two lessons because they go together. 74, go to Kramer's rule. All right, now basically in Kramer's rule, when they introduce Kramer's rule, they're going back to this section. Well, hey, Duncan. Duncan, all your quizzes are up there in the box with the answers. So you might want to go get those so you have them. Oh, except for this one, which I have. Okay, there you go.
Thank you.
All right, and the answers are up there. Okay, so now Peter slash. So let's do, just for, since we've already got this one on the board, let's go ahead and solve this same system for y. Okay, so we're going to come over here with a1x plus b1y equals c1, and then a2x plus b2y equals c2. All right, so we just took the same system, but now we're going to solve for y. And we're going to look for the patterns here, and then we're going to show you Kramer's rule. Okay, so if I take this generic and I want to solve for y, that means I want to get rid of x. So we're going to multiply this one by what?
Y. A2.
A2, and all the way across, and this one by
Negative A1.
negative A1. And those they're gonna cancel then, right? So here we go, all the way across. We got A2, A1, x plus A2, B1, y equals A2, C1. And then on the bottom, negative A1, A2, x minus A1, B2, y equals negative A1, C2. Peter, second slash. So now these two are going to cancel. Selena slash A2, B1, y minus A1, B2, y equals A2C1 minus A1C2. So then, next step, factor the y out to the front. I get A2B1 minus A1B2 equals A2C1 minus A1C2. All right, so now y equals A2C1 minus A1C2 over A2B1 minus A1B2. All right, so everybody sees how we got there. Now, everybody turn to 74, and we're looking at Kramer's. So we're going to say this is 66 and Kramer's that we're working on here. When you look at the Kramer's rule, they're going through, just using different variables, the same development. Okay, they're going through the same development here, and they're coming up with a Kramer's rule. And basically on Kramer's rule, you're going to say x equals. Now you have two matrices, and then we're going to see how these two matrices go with these two equations, because I'm going to do the two matrices that are a little bit different from the book, because I'm using these as my examples. When you're using Kramer's, this bottom matrix is going to be your core matrix here. So you're going to have A1, B1, A2, B2. Wes, you may stop that voice. Thank you. A1, B1, A2, B2. Okay? That's always going to be on the bottom. And then we're going to, since we're solving for x, we're going to cover up the x, and we're going to replace the x coefficients with the answer coefficients, and they're going to move there in the place. So we're going to have C1, C2 here, because we're solving for x, and we're going to have the B1, B2 here. Okay? Now, what Kramer discovered was this cool pattern could be modeled by a matrix determinant over a matrix determinant. All right? So when I take the determinant of this top matrix, what do I get? C1b2 minus b1c2. Remember determinants of a 2 by 2. It's just this one, this product, minus this product. Okay? So I'm going to have C1b2 minus b1c2 over, now I take the bottom one, a1b2 minus b1a2. All right, now let's look at our x, and let's look at the x we solved for earlier. Okay, b2 c1 minus b1 c2 over a1 b2 minus a2 b1. If we know Kramer's rule, we can solve systems of equations without ever doing the work. Okay? Yes. All right. Yes, now that I've taught you, you may certainly use Kramer's rule. Now, look over here. Shh. Okay, I did all the work. I solved the system. I got down here, and I have my answer, right? So I'm going to use this so I can have some workspace. Okay, now, do what? No, I didn't. This was the same equation. I have my answer down at the bottom once I did all the solving. Now let's do Kramer's for y. Y equals, the bottom is going to be the core matrix here. So I'm going to have A1, B1, A2, B2. A1, B1, A2, B2. The bottom matrix will always be the core. Yes? Not right now. Because you're irritating. Okay, so then y.
Was that on tape?
Yes.
Oh.
So y equals. Now I'm going to do the same thing with y that I just did with x. Since I'm solving for y, I'm going to cover the y up. And I'm going to replace it with the answer matrix here. So I'm going to have A1, A2, and then in place over here is C1, C2. Now all I have to do is take the determinants of each one. So I'm going to take this one and get A1, C2 minus Wesley. Thank you. C1, A2, okay? And then on the bottom, it's going to be what?
A1, B2,
A1 class.
A1, B2 minus B1, A2,
Wrong.
okay? All right, so now look at the denominator, look at the bottom. I've got A2, now watch what happens. It looks like it's wrong, but it's not wrong. If I take A2C1, that's there. If I take A1C2, that's there. If I take A2B1, that's here. If I take A1B2, that's there. Basically, if I multiply that one by -1 and that one by -1, I multiplied by 1, it becomes that one right there. So the answers are the same. Okay? So basically, yes, if I have A minus B and then I have B minus A, this one's just a negative of that one, right? So basically, they're both flipped around, so that's just a -1 multiplied through, which is a 1 overall, because -1 over -1 is 1. And you get the same answer. Okay, so let's go, since Kramer's rule is so much faster, let's go back to the section we're doing. Okay, go back to the section we're doing. And you can do all of these using Kramer's rule if you choose. because you've now been taught Kramer's rule. And Kramer's rule is faster. Hey guys, what's going on?
The dropping calculators.
Yeah.
Okay, shh. Now, let's look at this one. Let's look at example 66.1. Look at that example. And it says, use abstract coefficients to find a formula for y. If I have 3x plus 2y is 8, and 4x plus 5y is 3, they're telling me to go back to abstract. We're trying to solve for y. Solve for y.
So we just don't listen to them.
So what they're saying, no, what they're saying here is to go back to your abstract solving for y to find the answer for y. Okay? But since we know that this is the same thing as Kramer's rule, we're going to do a little leap here and go straight to Kramer's rule. What is going on, guys?
That's awesome.
Okay, so detention. Who do I owe them to here? Come on, guys. Stop it. All right, whatever's going on, it needs to stop. You're being reamed out on the tape here. Okay? I don't want to give the whole class attentions, but it seems like just about everybody's involved. All right? So here we go. Let's apply Kramer's rule to solve for y here. So we're going to do what on the bottom?
3.
Y equals, we're going to have 3, 2,
4.
4, 5. And on the top, we're going to have what? We're solving for y, so we cover the y. Okay, 3, 8, 4, 3. Does everybody see how the one I'm solving for, I'm going to replace with the answers? Okay, so this is going to give me
9 minus 32.
This is going to give me, the top is going to be what? 9 minus 32 over 15 minus 8. Okay, so what is 9 minus 32? Negative 23 over 7. Okay, now, so that's my y. Okay, and that's what they got in the book.
Leave it like that.
Amazing. That's the answer. Okay, that's the y. Now, if we were going to go ahead and solve for the x in the same problem, we would do what? X is going to be
3, 2, 4.
okay. Now the 3 is not. Oh, you're talking about the bottom. 3, 2, 4, 5. See, the nice thing is once I've already solved for that, I already know the bottom is 7.
Yeah.
Right? Because I already solved it down here. I already know the bottom part of 7. So now the top part is going to be what?
2, 8.
8, 2. Right? We cover this one
Yeah.
and we put that one there.
Same thing.
8, 2,
3, 5.
3, 5.
40
Okay?
minus 6.
So now this is going to be 40 minus 6 is
34.
34 over 7 would be the y.
Do you know what that's to reduce, like, at all?
Well, negative 23 over 7 doesn't reduce. And 34 over 7 doesn't reduce either.
I mean, like a mixed fraction.
No, you don't have to do that. Now, as long as they are reduced, you don't do it. Okay, everybody go to our homework. So everybody pull it. That was through 66B.
What about
Everybody pull out your homework.
day shifts?
I know, we're going to have to do that one later, but right now we're going to pull out homework. So we need to do 66B tomorrow, but we're ahead of our homework anyway. Okay, so everybody pull out your homework and exchange lesson, the first one. Exchange 63. Exchange 63. And we'll cut this off.